Okay, good evening, everyone, and welcome to our second class for this week. Today we'll continue our discussion on memory and context management, and we've already looked at semantic memory and episodic memory. So today we'll be looking at procedural memory. Um, as usual, we will be starting with a recap of what we did in the last class. So who would volunteer to take us through what, just give us a summary of what we did on Tuesday. Nicholas, your mic is unmuted, but can't hear you.
Like, can you hear me?
Yes, I can hear you now.
Can you hear me now?
Yes, I can.
Okay, so I would like to speak about the episodic memory and the components of the episodes. So the episodic memory is a type of a long term, is heavily like based on consciousness and um, recollection of specific um, personal experience, events and situations which has occurred. So, and the component of an episode lies in the what, the where, and the when. So the what means the context. So in this context, maybe I might be referring to as like what maybe a specific car. So maybe I'm talking about the car. So the car is blue, and that is the context. The where. So the where is maybe the location that I saw the car. So the blue car. So maybe I saw the blue car at Abadi, and the when um, will be the time. So I saw a blue car at Labadi yesterday. So those are the um, components of an episode. Um, with the with the variant, I would think I will have to like go and like revisit my books. It like skipped me like within the point, within the instance. So if somebody could also help me to like recap, I would really be glad.
Okay, but what you talked about just now is about the episodes in episodic memory in general. Here we are specific to AI agents. So it's not an episode. Episode memory is not memory about personal experiences. In this case, it's a memory that captures a record of the agent's experience. So what has happened as the agent has been running. The memory that captures that is what we refer to as episode memory in this case, because we are specific to um, AI agents. And when I say components of an episode, I'm actually talking about what makes up the experience tuple. We talked about the experience tuple on Tuesday, which is, well, I mentioned that that's one way of modeling an episode. And I mentioned that the experience tuple comprises the states and action, reward, and the outcome, where the state is really um, it's a representation of the outcome, like I mentioned, would that actually be like the next stage, right? Yeah, I think it was next stage that was the term we used in the last class. Um, and I remember mentioning that the state is the environmental context of the the agent at the point it gets into the current node. Prior to the arriving at the current node, the environmental context, that is the state. While the action is the agent's response or to call, assuming it's a to execution node, the action that's the action. The reward is the outcome of that action or the user feedback. I remember at this point I mentioned that it's called reward or result, but the quality reward is more appropriate, or it's more fits more in reinforcement learning scenarios. And I remember Alana you asked some questions about reinforcement learning at that point. And then the next stage is the 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 state following that action. I mean, how has after the action, the state probably may have changed. So that state at the end of the agent's action is the next state. And then I also mentioned that the experienced people may also have some metadata like timestamps, user ID or session tokens or some other such metadata. Okay, so Olarawaju or Lawrence, would you like to give us a summary about episodic memory variants?
Okay, sir. I stepped out. I knew when he was speaking, but let me just add uh, my own understanding of what happened. I mean, what I understand.
Sure, go
Basically
ahead.
from okay, sir. Basically from the word episode. Episodic talks about an event. I mean the record of what's happened, the episode of the record of different episodes, different events. So, based on what you told us, is a clinical record of the AI agent's experience, which capture three W's: what, where, and when. And then it provides the context of the sessions. And you also give us to understand that, for instance, episodic memory. Um, I'm trying to remember now. Ask about four states. I mean components. I mean to say components. We call them the tuple, experience tuple, which
So
comprises
it's tuple. That thing is an L. Was it an I?
no tuple. Yes, tuple. Data structure. Am I right, sir? Tuple.
Yes, yes.
Yes, tuple. Experience tuple E, which stands for SARS. SARS. The S there is the state. That's the current context, the environment prior to any action by the agent to take. That's the current state per time. Then, based on that state that is perceives, then the A is the action that the agent will take. Really, or in response to perceiving that state, there might be the tool call or function call, anything that it does based on the state. And then the R there is the reward, or you call it the results, which is the outcome that it's resulting from the action that is taken. And then the S, the second S, which is like a transpose, I should say, S is that call it, you told us is the environmental context, following the agent's action. And these four elements form the components of an episode. And then basically, so that's what I can remember. Though you told us the experienced tuple can have some metadata like the timestamp, the user ID, the intent, and the tokens. These are the details that can be meaningful to capture an episode. So this episode's memory are the things that I see them like maybe that things that may enter into a log that the agent need to put in memory. And this
Yeah.
provides context for the sessions that will come time and again to know exactly what happened, what time it happened, where it happened, and the likes. So,
Well, that's a very apt word for episode memory log. It's essentially a log of the agent's execution. Okay, but what of the variants of episodic memory? Will
okay,
anyone take
okay.
that? You can if you want to learn about it.
So you said the variants are,
Yeah,
there's the various types, I guess.
yeah, yeah.
Uh, let me um, let me pause for a while, sir.
Okay, we actually Kenneth actually mentioned that um, just
Okay,
as before the class actually started, where he observed that at some point I was saying semantic memory when I actually meant episodic memory. You mentioned those that buffer and summary memory. That's what we talked about. Those are variants of episodic
okay,
memory.
okay. The two types. Okay, sorry, sir. The variants. Okay. Oh yes, sir. Buffer and yes, I get it, sir. Buffer and then the hybrid also.
Yeah, well,
Okay.
hybrid is essentially a combination
The
of
two of
buffer
them.
and summary. Yes,
Yes, sir.
Kenneth, you want to say something? Guys.
Please, I have a question. I don't know
Sure.
if like this is the right time, but okay. So, the the buffer stores stores the memory like for a short night time. Maybe I think like for like a temporal.
Mm,
Um,
Well, in
like I
this
don't know if this is
case,
right.
well, in the case of agentic AI, this is not
Mm.
the buffer you use to help smoothen variation in flow rate, for example. That's not that buffer in this case. Because that one like maybe when you're streaming where you try to if maybe the rate of arrival is higher than the rate of consumption where you keep the excess for what it's not that kind of buffer. Buffer memory in this case um, we keep a raw transcript. Well, it's still a buffer like that somehow because it's usually implemented with a fixed length queue. So when it fills up, when it fills up as more episodes arrive, the older ones get dropped off, just like a typical kind of buffer you're talking about. But the key thing here is not about that. Key thing here is that it keeps a raw transcript. If I could use a record verbatim the episodes as compared to summary memory, which um, re- captures a condensed version of the episodes. Does that address your question? Kind of.
Not really, sir. I think like, my confusion is the buffer. Um, it holds the information for a very short time, and it is under the episodic in my memory. So I was like wondering um, why don't we like put it under the short and my memory, and like so that it fits within how it's am I describing it, because episodic like stores like the memory for a very like long time. So if like there's a sub like variant, or maybe if like there's a sub like version under 8, then that sub should also store something for like a very long time than to store something for a very like like short like possible time. So like that's like my question, and like that's like my confusion. So
I believe
yeah,
I think
please
I
please do
mentioned
that.
that episodic memory is working memory. Did I mention that? Did I mention that it's working memory?
Yes sir.
So if it's working
Yes sir.
memory, I mean you don't persist. You typically would not persist information for a long term there, with persistent actually implies long term storage. So it's working memory, meaning that the contents change a bit frequently. I mean, for each episode, it's updated. In case of buffer memory, you append to it. In case of summary memory, you update the summary. So it changes frequently, right? Now, for the fact that the buffer memory is implemented using a fixed length queue, once it fills up, you drop it's like a FIFO queue. Once it fills up, the oldest episode gets dropped off to enable it to accept the incoming episodes, right? But assuming the agent execution is paused, and it's paused for 100 years, if that's possible, the buffer content will still stay that way for that 100 years that the agent is paused. But once the agent continues executing and more episodes get generated, depending on the length of the buffer, it will keep accumulating episodes until it fills up. At which point it starts dropping the oldest episodes while the new ones start coming in. So I don't think there is really any ambiguity here. It's working memory. That means it's relatively dynamic as compared to the knowledge graph or the vector store, assuming you use an actual vector database, in which case, if you shut down the agent, that information still persists and can be used by another agent that can be used by whatever other application. But in the case of episodic memory, when you shut down the agent, it's gone unless your agent architecture has provision for persisting the buffer, the episodic memory contents before shutting down. Does that make is that clearer now?
Yes sir. Thank you very much.
Okay, right. All right,
All
so
right.
we move into the meat for today. Um, Procedural memory. Uh, while semantic memory captures facts and episodic memory captures the agent's experience, procedural memory captures okay. procedural memory captures, how will I say, workflows, instructions. It's implicit memory. It captures how the agent should perform different actions. Now, it comprises policies that have been internalized to use protocols. For example, in the tasks that you have been doing, the state promotion tasks, many of you have been injecting the JSON schema, for example, then in the assignment or so, or code, or I don't remember, where we talked about tool use. I think we injected. You could inject the tool schema into your prompt template, right? By providing that schema, or in your case, the tasks that you've been doing, by providing the JSON output schema in your system instruction or your prompt templates, you're already telling the agent that this is how you should handle the output. You're already giving it a procedure for structuring the output. And so you're providing it with procedural memory. Reasoning patterns is also part of what comprises procedural memory. So essentially, whatever information that the LLM makes use of, that's available to the LLM, and it makes use of it, which gives it guidelines, direction on how to perform actions, it forms procedural memory. And procedural memory is not even just, it includes the weights of the LLM that powers the agent. The model weights form part of the procedural memory, because how the LLM responds to given a specific input is informed by its weight, by its training. So that also forms procedural memory, even though to change that, to specify that it's not as easy as providing instructions in the prompt, like specifying guardrails in the prompt, for example. So the procedural memory enables the agent, okay, in episodic memory, what it helps the agents to know is what happened, what happened, when, and so on, right? But with procedural memory, the agent is able to answer the question, how should I solve this problem? How should I respond to this? What action should I take given the current context? So it guides the LLM, in this case, the agent, on how to act given a particular state. So based on the state, the procedural memory influences how the agent acts, what actions it takes, and in what sequence it takes those actions. Does anybody have any questions so far? Okay, so we continue. Now, some of the things that make up procedural memory include SOPs, a standard operation procedure, which SOPs are like the agent's handbook, like instructions you provide in your prompt, say your system prompt, specifying how the agent should act. If when we talked about prompt templates, right? I think we had examples of this from our prompt when we looked at prompt templates towards the beginning of of this training. So such workflows that are defined explicitly in your system prompt, they form part of the agent's SOP. And then few short examples that you provide in your system prompt could also form procedural memory. Like you should provide different variants of input output pairs. They really help to teach the model that for this kind of inputs, this is how you should map, this is how you should map so and so input to so and so output, which is like telling it how to act given certain context. So such few short examples could become part of the procedural memory. Guardrails, deterministic guardrails. Now, chain of thoughts, for example, for a single LLM or for an agent, your specification, perhaps in your system prompts, that saying, I think we had something like that when in the demo code for tool use, where we specified that if the user query asks for if the user query asks for, I think, offset from GMT or something, and it's or when to answer a question requires some intermittent result value, which requires calling another tool. You should call the tools in sequence or something like that. By providing that guardrail, provide that instruction that specifies that this tool should be called in a specific sequence. That deterministic guardrail that you're providing, or even specifying that you should always call tools in parallel, assuming that's what your use case requires, or that you should never call tools in parallel, you must always call tools in sequence. I know I think we observed when we were trying to code that there were some models that would always call the tools in sequence. That is their procedural memory. Even when we specified in the system prompt that if the result of two tools are if two calls are not dependent on each other, then call them parallel. Some of the models we tried out, the system would always call them in sequence. Some of the models would always call in parallel, even when one tool requires the output from the other as its input, and then it will just hallucinate that input that is supposed to get from the other tool. So instructions that you provide in the system prompt to ensure that the agent follows a strict procedural sequence in its action, those are deterministic guardrails. They also form part of the procedural memory. Now, procedural memory, it helps to reduce hallucination, workflow hallucination, in that it provides a clear, structured manual instructions to guide the agent's action in giving in specific scenarios. So they help to minimize the agent hallucinating the actions it should take and the sequence in which it should take such actions. Does anyone have any questions so far? Okay, we continue. Now, tool users procedural memory. I've hinted at this in the introduction. So when tools are like muscle memory, right? when you do something repeatedly, you as a human, when you do something repeatedly, most often it becomes muscle memory. So that when you want to do that same thing, you don't really think about it. You just do it because your body has become accustomed to doing that. So tools are like they they provide that kind of um license capability to the model. I mean, the model wants to, let's say, call this API, and there's already a tool that does that. The model doesn't need to think about how to go about, or okay, let's say the model needs to retrieve news from a certain platform, and there's a tool that wraps it calls to that platform API. All the model knows, hey, from the tool schema, it knows that when you call this tool in so and so way, you expect to give me this response. It doesn't bother thinking how that goes or what. All it knows is it just calls, or at least it makes the tool call request, and it expects to get the response. So it becomes sort of muscle memory. And then dynamic tool selection is, let's assume you have so many tools available to the model. Usually you would inject the tool schema into your system prompt. But at some point where you have so many tools, it's not feasible to do that because the context, the model's context cannot handle that large volume of information. And that's where two libraries come in. So with two libraries, you have all the context in this about the tools, documentation, tool schema, and all that. And when the model needs to invoke a tool, actually to make a tool call request, it performs like a RAG search. RAG is retrieval augmented generation. It performs a RAG search such that it will retrieve, it will be able to detect, the result of that search will give it the most appropriate tool to use for what it wants to do, as well as the information about that tool, like the schema. And at that point, it can now make the tool call request. That way, the agent learns about the tool dynamically. That's where just-in-time learning. It learns about when it really needs to use. That's when it learns about. That's when that information, as it retrieves it from the RAG request, RAG search, it injects it into its context, and so it learns about it just in time. Now I'm combining about 3 different points here, and so it can dynamically select tools from the library such that it's only the tool, the information about the tool, the specific relevant tool at that point that is injected into the context of the model. But if you had tried to inject all the information about all the tools at once, you will overwhelm the context of, I mean, context is finite, right? Is that clear? Does anybody have any question about this so far? Okay, go ahead. Now, self-correction. In the stage 4 task, I believe you had to implement the reflection loop where the model, the agent generates some response, and it critiques that, it critique node evaluates that response and weights it, and then based on the evaluation of the critique agent, the agent, the critique node, the agent may output that request if the critique node certifies it okay, or it might go through a reflexive loop where it tries to fix whatever issues were flagged by the critique node. So that by building the agent such that it follows this procedure, that process, whether from including the prompt, your the agent, your edges and so on, that make this reflexive cycle, this feedback cycle, this learning pattern that make it possible, forms procedural memory, because I mean it tells the agents implicitly anyway, in a situation where if you generate an output, you evaluate it. If it meets, if it's up to the bar, you output it to the user. If it's not up to the bar, you go back and refine it. That is a workflow. And so the specification of that workflow of the of that workflow forms procedural memory. A multi-agent systems, instead of a critique node, it would be a critique agent. So and that critique pattern, reflection pattern, well, they are related, because with the critique pattern, you typically would perform reflection unless your so in a multi-agent system, you wouldn't have a critique node, you would have a critique agent or something, as choose to call it. In essence, that workflow that you define, both through your edges, both whether implicit or explicit edges, it will be an implicit edge if you use an edgeless graph, both through your edge, your graph structure, both through your prompts and so on, that forms part of the procedural memory. Any questions so far? No one is asking any question. Any comments? Okay, we move ahead. Dynamic skill acquisition. Now, if from the perspective that procedural memory is about how to take action, how to solve problems, how to approach certain intents, how to act in specific contexts, procedural memory could enable the agents to acquire skills dynamically, acquire skills at runtime. Remember that skill can also is one way of saying tool. Skill in this case is what it can do. Now, like when we say tool library, those tools are skills. Now, the agent learns about those tools at runtime when it needs to use a tool. It tries to search, tries to retrieve the space, search for the best tool, and it retrieves the information about that tool from the library, enabling it to now make a tool call request when it's able to identify the right tool. Now, assuming the agent, say, in a given run, in a given turn, it was able to generate some code which successfully addressed the user's request. The agent could dynamically learn that for so and so kind of requests, this code or code in this structure is appropriate. So if it learns that it's not code snipers function, even reasoning parts, for this kind of problem, this is how to reason through them to achieve the optimal result, to achieve the user intent. If it learns those, and it can dynamically, depending on how you build it, you can dynamically capture that information that for this kind of problem, this is an optimal way to solve it. It has acquired a skill. When next the user makes a request that is similar to that particular one, the agent already knows how to do it. It goes ahead. That's like reinforcement learning, learning by doing. When it has done something and it identify what works, we can capture that, and next time it doesn't need to go reinventing the wheel. It already has captured that for this is the best way to do it, and it makes use of that skill that it has acquired. So essentially, it identifies successful approaches to solving given problems or category of problems. It stores those successful approaches. It persists them in some form of storage, so that in future those become assets that you can retrieve in future as guides to solving similar problems. And then on your own part, when you have, say, written a script or a function to solve a particular problem, if you now package that function as a tool, you have essentially converted that one-time solution. You wrote that function to solve a particular one-time problem you encounter one time. By packaging it in a tool, you're making it possible for that solution to be reused. And so the agent can call that tool later, and that tool becomes part of the procedural memory. So you can also build an agent that can do this. Agent that can create its own tools, even though you have to provide it with the capability of invoking those tools that is created. And such agents can dynamically acquire skills, including tools, including successful approaches to solving problems, as well as even non-successful approaches. I mean, if the agent had tried this approach and it didn't work, it can capture that as, hey, never do this way. For example, you ask the agent to make coffee. Let's assume the agent is, your house is a smart house, and the agent controls the house. And the agent turns on the TV, first of all, making coffee, turns on the TV, opens the windows, and then no coffee is made, and you provide feedback, hey, that's not how to make coffee. The agent has learned that turning on the TV and through the windows has nothing to do with making coffee. So next time we ask for coffee, he knows that you shouldn't do that. And if it eventually learns that to make coffee, you turn on the coffee machine, you really do that, and it's successful. Next time, it doesn't need to learn that, it has already acquired that skill. It goes straight, no more trial and error. Because he has already gone through the loop of, I tried this, it didn't work, I tried this, eventually I tried this, it worked. So he has captured information on the output that actually worked. So next time, he doesn't have to go through that trial error. He already knows how to perform the action that he requested. Questions, please? Okay, we continue. Meta prompting. Now, so far, you've been writing the prompts for the agents, right? And the agent just executes those prompts. Now, meta prompting is a strategy, is a way for the agent to write its own prompts. the agent can prompt itself. It allows the agent to, well, it can prompt itself now or other agents. Prompting itself would be to optimize its own prompts. For example, it knows it has tried with the prompt it has and it didn't work so well. It can refine that prompt to make it more appropriate. And so the agent is able to dynamically write prompts for itself or for other agents in multi-agent systems. And that prompt that the agent writes is forms part of that he writes or rewrites forms part of procedural memory because it essentially provides a guide on how the agent is supposed to act. For example, if your original prompt says always provide long responses, or you didn't specify that the agent should be concise, you just said answer the user's question, for example. Okay, someone has a comment. Answer the user's question, for example, and then the agent tends to be verbose, but the feedback it gets is that the user is not satisfied. Maybe you give it the feedback to always be concise. The agent can update each prompt, adding the instruction to be concise. And that update to the prompt, inserting the instruction to be concise, is meta prompting. The agent, an agent prompting itself or another agent. So that process of meta prompting involves self-referential logic where the agent is prompting itself. It allows the agent to dynamically optimize its prompts, dynamically optimize its actions, its operation, its procedures. That's just essentially what meta prompting is, and it's an approach to procedural memory management. Any question? Oh, okay. Kenneth, go ahead.
Oh, okay, sir. So for this, for the meta prompting, are there circumstances that it has to be used, or it can be used whilst creating any agent? Because I'm okay. So like for maybe like for my case of creating a social media and my discipline. So like, do I need to use the meta prompting, or like there are cases where I'm supposed to use it based on the kind of memory that is being used?
No, it's not compulsory to use it. You need to determine whether your use case warrants it. I mean, for the agent for the agent to meta prompt, you have to build that capability into the agent when you're at the point of where you're developing it, right? So you, the architect of that agent, has to determine whether or not it's of any value in that particular agent. It's not that you must use it. The idea here is know what is possible, and then for your use case, decide what and what should you do. Yes, meta prompting adds some level of complexity into the agent. Do you really need that complexity? If it's beneficial, of course, you should use it. But if you can achieve optimal performance without meta prompting, then there's no need to um there's no need to use a sledgehammer to kill an ant.
All right, sir.
They were Okay, so I think at this point, okay, from episode to procedure. So through this class, I've been talking about the agent learning from its experience, and based on that, updating instructions, um, learning rules, persisting those rules, or prompting itself, and so on. Essentially, this involves a distillation process where the agent learns from its experience, like from its episodic memory, it can identify patterns, it can extract those patterns, and it abstracts those patterns as rules. That is the distillation process. It's like a maturity model of the agent's memory. That's essentially what I've been describing in most of today's slides, where the agent learns dynamically from its experience, and based on what it learns from its experience, it updates its procedural memory. So you identify patterns in the episodic memory, you extract those patterns and capture them in your procedural memory as rules. That way, the agent learns and dynamically improves its capabilities and performance. Um, Another way of moving from episode to procedure is that you yourself, the developer, observing from the agent's runs, maybe test runs or even actual runs in production, um, patterns that would be helpful if captured in the agent's procedural memory. You extract those patterns, abstract them, and put them yourself into the system prompts. For example, that instruction about in the scripts that we use as example for tool use, the directive to call tools in parallel if they are independent, and that when one tool depends on the output from another tool, they must be called in sequence, and so on. That it came about from previous runs I had of that script, particularly based on the model that was being used. I observed that the model had non-optimal performance, and so I had to add those guardrails to guide the model's action. But for some other model that's able to infer this, you may not need to do that. So hard coding would really depend on your specific agent's architecture. What model are you using? How is it built? What is not working and what is working? Based on that, you can update the system prompts with you can update the what's the term, the workflow as specified in the system prompt, and by so doing, you have updated the procedural memory. And then there's fine tuning where, based on data from the agent's runs, you can now use those the data points to which we train the model, fine tune the model, even in reinforcement learning with human feedback. When you do that, what you're really trying to do is to bake those procedures into the agent's, the agent's weight. In this case, the agent will be the weight of the model powering the agent. And so you have hard coded it into the model structure itself. And it becomes subconscious procedure because That's just how model works. Any question? Okay, we move ahead. So at this point, I'm going to stop sharing for a short while so I can share my IDE and we look at the demo code. Please let me know when you can see my screen. Is my screen visible yet? Okay, thank you, Lawrence. So, yeah, Kenneth. So these first two lines disable that warning, so it doesn't get to show when you run the code, right? The warning you talked about. All right. So here we are essentially the imports are essentially the same imports that we had in previous um demo code that we have. I'm trying to see whether there's anything new. Okay, the only new thing here is remove message. Excuse me. What this does, but I think we encountered that when we encountered that when we had hybrid the code that about buffer and summary memory hybrid. So it's nothing new, I guess. And the configuration is the same that we've had. I'll just get to where we have something different. Yeah. So here we have a pipes digs that we are using to capture our procedural memory. Well, you can actually persist what the information that this ob object captures. Of course, when it's stationary, it's an object. Um, you can persist that in maybe a vector database or whatever the case may be. But um, we are using this to capture our procedural memory in the state, the agent state. And so here we have procedural memory as a list of procedural rule objects. The rest of the states is what we already have from previous runs. And we still have our helpers to classify intents, to extract triples, to contextualize the query, and thereby, based on the history on the episodic memory, to extract entities from a given text, which is useful when we want to interact with the knowledge graph, to evaluate importance, which we also used in the demo code from last on Tuesday, even this get to retrieve the top K items from the knowledge graph, and then the nodes, retrieval node. Our retrieval node is essentially the same as we had in our code for episodic memory. The same with the config resolution node, the same with the researcher node, the writer node, critique node. Yeah. The where the main difference comes in is this meta reflector node. So the meta reflector node allows the agents to learn from its episodes, and so it's able to capture rules. It's able to identify patterns and capture rules, which it stores as procedure. So the prompt for the reflector is simply asks the node to extract an SOP from the critique that the critique node generates. And this meta reflector node runs right after the critique node. And now here it includes an example which is still part of procedural memory, because this example is guiding the kind of output you want. And here you have a guardrail, an output guardrail that says output only the rule string. I can even make this a tighter guardrail by specifying that it should not include any introduction or explanation or prelude or postlude, to even make it more ironclad. Because some models, even when you said I'll put only the rule string, they'll still tell you here is the rule string. They'll give you the rule string and they'll now start explaining it. So this guardrail, this example, they still form part of procedural memory. So even in the nodes that is helping to update to the procedural memory to generate SOPs, we are still using procedural memory as part of the prompt. The new rule is persisted into the state. Of course, here we are putting it out so that we can view it as the agent is executing. The save memory is more or less the same that we've had in the previous code, particularly the one for hybrid of episodic, buffer, summary, as well as semantic. And we build the graph. We use an edgeless graph, and then we execute. At the first turn, there is no rule. Here we're not we're not persisting the learned rule. So once the agent terminates, it's gone, right? So at the first, but if you build your agent so that the rules are persisted, then at this first turn, it won't be no rules yet. Probably the agent will probably perform some RAG with some retrieval of rules, of relevant rules, to guide it in achieving the specific intent from the user's query. So the first query is saying give a detailed 5-paragraph history of Tanzania. Now, while this turn is running, the agent is going to learn rules from the critique that the critique node provides. And then those rules is going to apply them in turn 2, where the user asks, now tell me about the capital. So the rules it learns would already be part of its context at this second turn, so that whatever those rules say it should not do, it's expected that it won't do it in the second turn. Whatever the rules recommend that you should do, it's expected to do those in this second turn. So now let's execute the code. The interesting part here will be from the critique node evaluating. Okay, I guess we should start from the output of the writer. The writer says the history of Tanzania is a complex and multifaceted narrative that spans thousands of years, and so on and so on. And the critique says the draft provides a detailed history of Tanzania, covering its early inhabitants, colonial period, independence, and recent developments. However, it lacks specific dates and events for some periods, and transition between paragraphs could be smoother, etc., etc. Now, the meta reflector is able to extract a rule from this critique, and it says the rule is always provide specific dates and events, ensure smooth paragraph transition, and so on and so forth. And then, because the critique did not pass the draft, it goes back to the writing node or writer node, which is the architecture of our graph. And now, as it's writing the second attempt at writing the draft, it already has that procedure, the rule that it has captured, and it would implement, or it should implement that rule in this second time it's writing. Oh, I actually need to check if we actually incorporated this, considering this, but I think we did in the writer notes prompt. I'll check that after analyzing this output. So the critique node also does not okay the second attempt. I think one of the issues we flagged is it could be improved by adding more specific details about major events, figures, and cultural development, and so on. And so the agent, the meta reflection node, now learns another rule. Always ensure that written content is engaging, blah, 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 blah. And so the third time, it goes back to the writing node to refine the draft again. And this third time, it's either that the critique okays it, or that we have exceeded the specified number of revisions. And so it persists the information that the knowledge that it has identified from that draft, and it ends that cycle by printing out the output as we specified in the graphs. The next turn, the question is now tell me about the capital. Well, this from the episodic memories, I was able to figure out that it's talking about the capital of Tanzania and so on. But our interest here is really from um, um, okay. Now, in this case, when it's writing, already the agent has those rules he has learned. And so it applies those rules in writing this draft. And you can see that because he has applied all those rules that he has learned, the critique note okayed this one. It didn't even need to go for any revision, which would suggest that the previous term terminated because the critique note okayed it, not just because he had exceeded the maximum number of revision. And so, as usual, the agent persists the information that he had extracted from that draft and we print out the output. So I guess this confirms that we actually implemented the logic to apply the rules in the right writer note. Any question? Was anybody able to, has anybody been able to run this code? What was your experience? Did you try to try any variation in the input queries and how did that go? Okay, I take it to be that there's no question and that nobody has tried the code yet. Please, I would like to request that you actually try to run all these code examples. Try to run them. Try different input combinations. Try to tweak the code based on what you observe. Because actually doing that, that helps you to get agentic AI development at your fingertips so that you'll be able to apply it and you'll be able to abstract it to other scenarios different from exactly what we have looked at and done in the class. And so, if there's no further question, I guess we'll wrap it up here. Please note that the stage 5 promotion task is already uploaded, and the deadline for submission, I believe, is I believe the deadline is Wednesday, next Wednesday. Please try to submit in time. Okay, that's fine, David. If you have issues installing your 4J locally, you could try using the cloud service or RDB. Even though that one will have some limits, but I guess you will not get to hit those limits in the class. All right. It used to be there. All right. That's it for today. I wanted to say, ladies and gentlemen, and I see that Adobe, who was here, has left. Okay, I think she mentioned having a network being flapping up and down. So we call it a night. See you all next week when we continue our discussion with agentic retrieval and context management.